Hi guys, we're about to start calculus. So here are the first set of notes for calculus. I'm going to pop them up in sections instead of a whole chunk this time because I want to gauge how we're going, and I'm going to write notes and alter them along the way. So as usual, there's the little smiley faces, or I guess our aims of what we need to achieve during the course of this topic. So you can go through those and tick off as we get to them. We'll look at those at the end. Okay, so we're working through chapter 8 of the Cambridge textbook, so the usual textbook, the one that you have at home. And the topic is calculus, but we're only going to be looking at a particular kind of calculus. So I've called it Introduction to Calculus, and we're going to be looking at differentiation. So I'll just read through these notes to start with. Calculus is a topic including parts called differentiation and integration. Differentiation, which is what we're going to do, looks at the changing steepness of a curve, while integration looks at basically the area underneath a curve. We're going to have a look at new symbols, lots of new language, while we start to look at calculus. Now, I like this next section. It says the calculus, or the study of calculus, is important in developing the student's ability to solve problems involving algebraic and graphical representations of functions and rates of change of a function. That probably doesn't make sense yet, but that's where we're headed. But it has a lot of relevance to a lot of fields out in the real world. A lot of quantitative fields such as physics, chemistry, medicine, engineering, computing, statistics, business, finance, economics, and the construction industry. Although you won't see calculus in those areas in the HSC in other subjects, it will only be maths at the HSC level. If you do go to study at uni, a lot of those different areas will look at calculus and calculus related things, particularly your economics and finance, which looks at econometrics and some of that style of calculus in there. So it is a topic that you will most probably definitely use again. Okay, so we will start with year 11 looking at differentiation. The other one, integration, we will look at in year 12. If you're doing the extension 1 maths, we will look at that in greater detail, and we'll look at partial differential equations and a whole heap of different things as well. Okay, so let's have a look at the parts, or some of the new words that we need to look at. Chords, secants, and tangents. The main one we're going to be looking at is tangents, but we'll talk about both of those. You may have seen some of these before, possibly. I'm not sure actually if you actually have seen these before. We'll use chords, secants, and tangents when we look at circles as well, but particularly tangents with this one. So a chord is an interval joining two distinct points on a graph. So we've got a parabola over here. We're very familiar with that from our functions topic. There's 2 points that sit on that parabola. A chord would just be a line that joins those 2 points. A secant, or a secant, I normally say secant, is not a word we will use much at all, okay, but it's good to see. Secant means cutting, and it's a line through 2 distinct points on the graph. So A and B are on opposite points, and the secant would go through A and B, and it's cutting through the axes through there. The one we are going to be looking at is tangent. Tangent is important. We're going to refer to the tangent a lot. The tangent is what we are dealing with when we do our differentiation. So informally, a tangent means touching. So you can see our tangent here. It's a line that is touching that parabola, and it's actually touching it only at one particular point here, and that's at point T. The definition here, it says, think of a ray of light from a headlight of a car going around a bend. Yeah, you can think of it like that. That's sort of what it looks like. We're going to look at it algebraically and graphically. And we'll deal with that word lots, but we'll deal with it when we look at circles as well. Okay, so if you've already had a look at the textbook, and I know a lot of you actually have, it's chapter 8. It starts with 8A, which is called First Principles. Now, I'm not going to start with 8A. I'm going to start with 8C and look purely at more of the algebraic side of differentiation. And then when you kind of are a little bit more familiar with that, we're going to go back and have a look at 8A. I don't like to do it first with 8a because I find normally students do not understand anything that we are talking about. So we're going to start with 8c. So we're not forgotten 8a and b, but we're going to look at that soon. Okay, so 8c, a rule for differentiating powers of x. Okay, so while we're looking, before we have a look at this rule for differentiating, and we're going to use that word a lot, differentiating a power of x, we are going to think of it algebraically, but I'm going to jump back to the graph up above as well. So we need to know what a tangent is. So I've got a parabola on this graph up above, and a parabola has a power of 2. So we have like an x squared in there. And a tangent is a line that cuts that parabola at one point. Okay, so we're dealing with a tangent all the way through this. When we do this thing called differentiation, what we're actually doing is we're going from an equation for a parabola, and we're moving to an equation for a tangent to that parabola by doing one algebraic move, basically. So let's have a look at what that is, and we'll slowly start to come to terms with what it actually means. But first of all, we're just going to learn a bit of the algebra behind what differentiation means, do some work with that, and see how we go and see what we need to go over again. Okay, so it says here, a tangent to a curve can be determined by differentiating the function. So we are going to have a function, which we're going to call f of x, like we normally did. We're going to do this thing called differentiate it, and then we're going to get a tangent to that curve. Okay, so if you need to, you can jump back up to here. So we have a parabola here, and we have a tangent to that parabola. Okay, the tangent shows the rate of change of the curve at that point. Now, we haven't looked at what that means, that rate of change yet. We're going to get to that, but that's just there, and we'll look at that over and over again. So you don't need to worry about that too much to start with. A tangent to a curve can be determined by differentiating the function. Okay, while it's useful to think of the derivative in terms of graphs, which is where we're going to be heading, it can be determined purely algebraically, and that's what we're going to have a look at today. We're going to start by looking at the algebra methods without considering what the function looks like, and this can be done through the use of certain differentiation rules. So that's where we are today. So let's have a look at this. The derivative of any power of x. So the derivative we get by differentiating. So we might write that in there. We'll write that. The derivative is found by differentiating. Now, we're familiar with a lot of this terminology. We've got f of x, so our function. We're used to f of x. We also called it y. Okay, remember our f of x was also y. They're the same thing. They're just different notations. So our function is equal to x of n, where n is any real number. Then the derivative of that function, we're going to call f with a little dash in there. There's a little dash up there, and I call that f dash x. And what we do is we take that n that's up the top and we pop that n down the front. We've still got our x, and we have our power of n, and we take a number away from it. So the n comes down the front and one number is removed from that power. This is usually memorized as take the index as a factor and reduce the index by 1. If you don't want to use the word index, you can use the word power. So there's a rule written again. If f of x is x to the power of n, f dash of x, which is our derivative, so we've differentiated f of x to become f dash of x, the n goes to the front, we've still got our x, and we get n minus 1. And we're going to have a go at some examples of that in a second. Notation-wise, this little f dash of x here, we're going to learn that we could write it as y with a little dash. We're going to write it this way with a little, and I'm not going to talk about this today, that's going to be where we look at it at first principles, but dy dx, and this little triangle, which is delta y over delta x, and we'll explain what that means. You may have seen that in physics before. And this one we don't see too often, f of x, and we've got extra brackets around it. They're all that first derivative. So let's have a look at doing that. Differentiate each of these functions. Okay, so I've done a couple of them here. So we've got f of x here. So by differentiating it, we find f dash of x. That 5 comes down to the front to become 5x. I take 1 off the 5 to become 4. That's it. Step 1, done. Let's differentiate the next one. F of x, our first derivative, or our differentiated f of x becomes f dash of x. The 8 goes down the front. We take 1 off the 8 to become a 7. So we get 8x to the power of 7. F of x equals x to the power of 37. Let's differentiate it. We get f dash of x. 37 comes down the front, x to the power of 36. So step 1, that's it. That's how we differentiate single functions. Okay, what if we have combinations of functions? What if we have our function being the sum of two different functions? Then our derivative is just going to be the derivative of each of those functions separately. If our function has a number outside the front of that function, then we just put that number out the front of what our derivative would be. Let's have a look at how that works out. Okay, let's do some. Example 6, we've got the question asking us to differentiate each function. When we're differentiating, okay, we want to find our f dash of x. That's what it's wanting us to do. Okay, so our f dash of x is going to be equal to, and we're going to do this to each of those separate terms within that function. So I differentiate x squared, it becomes 2x to the 1. I don't need that power of 1, so I'm going to get rid of that. So we're not going to put the 1 in there. I differentiate 3x, so there's this imaginary 1 out the front. Okay, the 1 comes down to the front, and 3 is going to times by it. So it's going to be 3 times 1. And my x, let's think of what happens. It's actually got an x to the power of 1 there. So if I take 1 off that, I get x to the power of 0. And x to the power of 0 is just 1. So that's all I get for that, is 2x plus 3. 5 stays. We don't get anything with 5, because what's actually happening there is it's 5 times x to the power of 0 is really what's happening. That 0 goes down the front and times it by 5 and I get 0. So I don't need to add a 0 here. It just becomes 2x plus 3. Let's have a look at the next one. Pause it and have a go at these yourself and then check with me to see if you've got the same as me. Here's what I've got for B. We've got f of x up here. So my f dash of x is going to be 4 times 2 is 8. X to the power of 2 minus 1, which is just 1. So I've got 8x minus 3, which I've got here. When I differentiate, there's a 1 in the power up there. The 1 gets times by that minus 3 to become minus 3, and the x disappears. Why it disappears, remember, is it's x to the power of 1. 1 minus 1 is 0. X to the 0 is 1. And the 2, we don't. It goes to 0, so we can don't include that in there. Okay, next one. Again, pause it, make sure you can do it. Differentiating this function here to get my f dash of x. 10 times 3 is 30. X to the 10 minus 1 is 9. Plus 9 times 4 is 36. X to the power of 9 minus 1 is 8. That's where that comes from. Like last, f of x is equal to this function. Let's work out what f dash of x is. 6 is going to times by the half. 6 times a half is 3. X to the 6 minus 1, which is 5. Minus, we've got 1/6 to differentiate that. 3 comes down the front. 3 over 6, which is a half. X to the 3 minus 1, which is 2. Okay, let's see if we can fit the next one into this video. Expanding products. Sometimes a product needs to be expanded before the function can be differentiated. Example here is 7, and we're going to differentiate each function. So we want to find f dash of x. The rules will be exactly the same, but what we need to do is we need to expand this out beforehand, and we need to expand this one as well using your FOIL method. Once we've done that, we can differentiate it. So pause it there. Check you can do it. I've expanded this to become here, and then we're going to differentiate that. Okay, by differentiating, this is what I end up getting as my f dash of x. Let's go and expand the second one and then see if you can get the derivative, and we'll just check with each other's answers. Okay, so I've expanded the first one, taken the derivative, and that's what my answer is. I'll upload this video and I'll make a second one with the rest of the work.